Maybe I put it somewhere, who knows? All right.
We're recording.
And after my presentation, you can cut off, so we don't have to record the same the meeting. Okay, thanks. All right, so I'm going to talk about the computational thermodynamics and its applications. Some of them are related to this project, but some of them are general. And I used to ask them a question: what are the materials? What are materials properties? Right? What do we really mean by that? It's actually turned out it's the response of materials to external stimuli. You change it inside the states of material. For example, if you heat it, if we do the work, or if the mass. So we have three types of energies, which is the heat and the thermal energy and work. That's mechanical, electric, or magnetic energy, or the chemical energy with the change in mass. Of course, you can do nuclear energy and so forth, but that's not in our research. And it turned out if you think about the properties in this way, it's actually all related to the derivatives of free energy. One way or another, some are direct, some are in few steps. Okay, for example, the free energy with respect to temperature, the thermal, or the mechanical, electrical, magnetic, and the chemical. And it turned out thermodynamics actually concerns all of them. It's the state of a system, the response, and with the stable, metastable, and with the interaction with the surroundings, basically the external stimuli. So I wrote a paper last year, summarized our work, and also in more general, the field in the last 20 years. I think it started like, I started Penn State 1999. So it's about 20 years. So I decided to write it. Was because I gave a talk at a TMS as my human rights reward. So I decided to write it up. So as you can see that it's like close to what, 47 pages. And it actually didn't take a very long time to write. I wrote it during the last day Thanksgiving, Christmas time. I finished it during Christmas almost. I submitted in February and get published in August. That's not too bad. So what do I have this one? In this paper, actually three major areas. One is the stability, metastability, and instability. That's people conventionally call them thermodynamic properties. Then I went into the kinetical properties, diffusivity, Seebeck coefficient, and so forth. And then I talked about the mechanical properties too. I started with elastic properties and the top of dislocations. And then the most recent work with Professor Bees on this stress strain curve. That's the latest one we have. And if you have learned, if you still remember thermodynamics to learn before, there's one impression most people got was that thermodynamics is for equilibrium only. So I have a slide, is that true? First says no, it's not, because the first law does not concern equilibrium only. It concerns changes, right? So it's not equilibrium. However, then the second answer is yes, it's for equilibrium only, and because Gibbs did it. Okay, Gibbs made it to equilibrium only. So if you look at the two equations, that means something is missing. So what's missing here is the d-Xi term. Okay, that's the internal processes. And this is represent all kinds of processes, not just one. You can have many processes in the system. Just use one term to represent it. The reason is because when Gibbs derived these equations, he focused on equilibrium only. So that means this is zero. Okay. Of course, we do not use internal energy. We use Gibbs energy. We call it free energy, all kinds of free energy. That now you really have to do is that basically put the Xi as a parameter. Okay, if you put Xi as a parameter, then it becomes a non-equilibrium system. If your Xi is not a variable, then it's equilibrium system. Okay, that's a difference. That means we have to model the Xi here. So what's Xi? Xi is the internal state variables. It's what you define the inside of the system. Because here, there are all three terms here. They're all from external, exchange with the surroundings. Only this guy, this term, talk about the internal. Okay. So that means we can generalize it. Of course, we can talk about the mechanical work. We talk about the electric. We talk about the magnetic with Xi. And here you can draw actually 3 terms with the first order, second order, third order, which the first order about equilibrium, second order talking about the stability, third order talk about critical points. You put them together, you talk about actually everything we have in a system. So what it means is this chart shows that you can talk about metastable because it's more stable, and the D2 becomes positive. That's stability is stable. Then when D2 equals 0, then you get the limit of stability. When D2 is less than 0, you get a unstable. So that means now you can actually use this energy curve to represent the metastable, stable, and also the kinetic barrier. That's actually why we wanted kinetics, because if you can get the energy curve, then we can get the kinetic coefficients. You can predict all kinetic coefficients in principle. Okay, so that one is very little used so far. That's why we want to explore that one further. Same thing is actually for the mechanical property. Mechanical property is that when you move the dislocation, and when dislocation to the unstable state, you can jump over. So that's what dislocation moves. That's how we worked with Alice and Bees to derive those parameters and put into the crystal plasticity. Okay, so that's actually come to the same figure. So this figure is very, very powerful because psi could be all kinds of psi. You can have all kinds of internal variables here. Okay, so example of internal variables, we'll give some examples. First one is actually talk about thermodynamics. Talk about the BCC alloy, B solution. If iron and copper form a BCC solution, and then you have to have the BCC copper energy. So that means it's a state you define, say, okay, if it's 100% copper, it's in BCC, what's the energy? Of course, we know it's unstable, okay? BCC copper is unstable at a low temperature, but you still have to get the energy of it, right? At the end, so that's one configuration. And then there's a lot of the order. Order is internal because you don't know how to control from outside. The polarizations are internal, and the defects are internal. Now, if you can model defects, then you can model all the mechanical properties, because mechanical properties are dictated by the defects we have in the solar system. Of course, the simple ones are vacancies, and they have dislocations, twins, stack and falls, green boundaries, phase interface, and surfaces. Okay, if you put all of them in there, you practically can describe all kinds of properties we have in the material. Of course, it's not easy to get all those parameters into it. And then to do that, we use Kaplan modeling to model the free energy. It's basically to model the free energy with the Gibbs energy as a function of temperature, pressure, and the composition, and the psi. Okay. So that's very important. It's the Kaplan model psi, like a FCC copper. Of course, you can debate how to do it, right? That's still a lot of ways to do it, because in unstable state, you cannot get the energy accurately. And then we do have a Kaplan community. We have a conference, annual conference. We have a private foundation, and we have a journal. Okay, so yeah, I see that you can see it started in the 1970s, and it has been growing and pretty stable. And we have tools. It's one Kaplan journal, volume 26 has described quite a few of them, and basically I have commercial ones. And for example, they claim that there are more than 1,000 users around the globe, most of the universities, and a lot of most of materials departments, and most of the materials companies. And then we have open source one. One is Open Kaplan, Thermochemica, and also that's our homemade Kaplan S-Bay. It's by our group. Our group has unique features. I'm going to mention a little bit is high throughput, and with uncertain quantifications. So that's different. And I want to brag a little bit about the Kaplan, the importance of Kaplan. It really supports ICME and MGI. So this is a quote from the ICME report in 2008. It states, Kaplan software is arguably the most important and perhaps the only generic tool available for ICME practitioners. That's because they provide the data for all simulations you need. That's basically the base of it. And then, of course, the MGI. It was initiated in 2011, and to enhance the computational capabilities, data management, and the integrated engineering approach. Of course, you look at it together, you can see the Kaplan will still be the base for MGI. If you want to read further, there are two papers. One is by Greg Olson and Charlie Kuhlman, and on the material genome from Harvard to flight. I wrote a paper about same year, a perspective on material genome. That's from my understanding. All right, so really what it does is that takes the modeling. I take the data to model this Gibbs energy. But what do we have? The input data is that we have two sets of input data. Actually, we only need one set. We only needed the derivatives, right? Derivatives integration will give you the function. So why is not enough for us? Because these measurements are related to heat. There's a big uncertainty, okay? So when you take this data to calculate the phase equilibrium, it's not accurate. Then you use the phase equilibrium data to refine the parameter. So these are mostly from experiments. And this is from nowadays is from DFT calculations and also EMF measurement, like done by Hojo Kim in our department. Okay. So when you do this one, you start with pure elements, you do the binary, you do the ternary, and then you make them into multi-component, and then you can do the derivatives, material design, and so forth, and calculate the properties. So now the properties is what we are focused on for our project. Okay. So to do that, we take experiment data, usually before. Now then we do DFT data, and then we do the statistical, get a final temperature. Now you see I have both the first principle and the experiment data. First principle data is very important because it not only speed up the experiment data, but more importantly, you can reach the metastable or unstable state. That one you cannot do experiment. Experiment where cannot reach those states. In this case, your data modeling will be much better because then your processing will reach the different states. So one slide shows the first principle calculations. Typically, you carry 0 Kelvin, that's 0 Kelvin energy. Then you do the vibrational phonon calculation. You got the phonon density of states. You got the another contribution. If for the metallic system, you got some electronic contribution. You get a electronic density of states, and put them together, you can predict free energy. So now it means actually from DFT, you can predict the temperature-dependent properties for a fixed configuration. Okay, of course, this takes time. As you can see that we started early 2000. This is our first paper, I believe, or maybe second paper about DFT calculations. We started with the temperature-dependent, take from the community. And then over the years, now we developed a high throughput code called the DFT.org, a density functional DFT density functional theory toolkit, which is open source. If you go to www.dfttk.org, you can install the code and do those calculations. And the DFT calculation still takes time. So we hired a new student, and he's here. It's Adam Krzyzewski, and they went to machine learning. So now it's close to 2 years now. And so Adam does the machine learning, and the goal is to speed up, right? So you do more faster calculation of the free energy. Energy at 0 Kelvin now. Hope we do free energy down the road. And then can also we call it transfer learning to extend it to other systems which you have no data before. So that's so this can be speed up dramatically, get the data. And then we did the PAC-HAFAT. You have to the open source modeling, high throughput modeling. So we develop a PAC-HAFAT code. So this is basically the calculate free energy. And then we have a lot of features here. And then we need to evaluate the model parameters. We use SPay. Again, is developed by our group. By now, I started with Richard, now go to another grad student. Basically, high throughput. Okay, 2 steps. And also a kind of robustness of the model, and use a Monte Carlo for the primary evaluation. Now you can do the uncertainty quantification. So in this case, now we have the tools built up. We have 4 tools, right? We have DFT-TK, we have the machine learning, we have the PAC-HAFAT and SPay. So that's what talk about is the WES. With those tools now, you can get any structure. We can get into some thermodynamic properties. Well, you can always make it better, but we have the tools to do them now. Then we can use this one to create a database, calculate phase stability. So we put these tools together, and this is our book, which gives the foundation, the theory. Then we have the data generation, as the machine learning and the DFT, TK. Then the data processing, and uncertain quantification. And we also give training courses. We do create, we form the Material Genome Foundation, nonprofit foundation, to give you short courses, training courses, as soon as the tools become available for teaching. So then we thought we should create another knowledge called the ocean of data, which we can take all different databases, combine them together, use the approach. We have to create a database, then do material design, this kind of cycle. Okay, this kind of cycle. We call it the data ecosystem. Idea is that I take experiment data, theoretical data, experiment data, and use this, we call it proto data, this input data. And then you do this process, you do the material design, then you do some experiments, you got data feedback. So this circle is important. So any new data will come back into the system. Then goes through the machine learning, then goes through the DFT calculations, then goes through the PyCap and SPay, and then we hope we even go to recycle side. Okay. So we have the tools now to do that. So the only missing part, not the only missing part, one missing part is where West comes in this one, this new project, want to do inverse design. So this is forward simulation, right? You cannot do, it's not for design. So we'll take the data and do inverse design, and then do more calculation, get new data into it. So that's basically, I could stop here now, but I have a few more slides. I want to talk this one is more properties, is more different properties, okay? So these are the second derivatives of the free energy. Give all the properties we have. A typical property we're talking about, heat capacity, some expansion, and piezoelectricity, and the permeability, and the permittivity, and so forth. These are all the second derivatives of free energy to different variables, okay? So we have been using this one, but there's a new set of data which we have not used before. Oh, yeah, I talk about the science properties. So the diagonal terms is all positive. That's a stability requirement. But the off diagonal terms could be positive or negative. Okay. So I believe we were the first one can predict those properties. We were the first one can predict negative sum expansion from complete from quantum mechanics. Okay. And then it turns all the properties could be have a negative sign, and they become infinite, diverge at the critical point. That's the limit of stability. Okay. We have theories. Now we have the tools to predict them. Okay. So property of the final temperature. How do you do that? It's the quasi-harmonic calculation I showed before. And then with the partition function, actually the quasi-harmonic calculation itself, it is a partition function approach to get the entropy. Okay. But now we can do a larger scale. One we can predict the negative properties, negative sum expansions, for example. We actually don't predict not a negative. We can predict infinity positive, infinity negative, and a zero. Okay. And they all be predicted by this quantum mechanical based partition function approach. So, but it's very important that, see, if you look at this, all these properties, right? As I mentioned before here, let me get this one. It's between a molar quantity and a potential. For example, this one is entropy to temperature, right? This one is entropy to stress. All of them is between this quantity to that quantity. However, there's not set of quantity has not been discussed. It's between the potentials. Okay, turned out there are a lot of properties there. So now I put one potential in the Gibbs energy function, we get chemical potential. So you can do chemical potential to temperature. That's thermal transport. Okay, chemical potential to stress, chemical potential to electrical field, chemical potential to magnetic field. Then the two chemical potential to the mole, of course, that's a thermodynamic factor. So this set of properties is a new property. That's what we use to predict a lot of other properties. Okay, this is just one chemical, one potential, right? But think about it, can have all other potentials. Okay, this to give us the called phenomenon called cross phenomenon. That's where Ansarg talk about his Nobel Prize. Okay, it's a cross phenomenon. And one of them is critical is the Seebeck coefficient. I sort of have one more slide. I must delete it. Maybe the next slide. This one. Actually, we have a lot of more properties. Look at this one. We can talk about the stress to temperature. Okay. We talk about stress due to the electric field. That's all other set of complete different properties. Okay. People always think you should do it by kinetic simulation, but turns out you can actually predict from thermodynamics now. Yeah. And also very important that this matrix is symmetric. So you can use Maxwell relation. This is very difficult to calculate, but this is very much easier to calculate. Okay. This is very easy to measure. So the blue ones you can measure easily. The black ones you can calculate easily. Okay, this is really important. So you can do experiment and then compare with calculation. And they calculate different things, different formula, but it gives same properties. Okay. I think that's probably my last. Then mechanical properties. That's one I really want to mention because it's really related to our work. This project. So we started with elastic properties. That's about 14 years ago. And Shuni, I went to a meeting. People talk about elastic constants, how hard it is. I said, wow, we can calculate it. It's easy, right? So why don't we calculate it? So I think I was at the meeting. I sent an email to Shuni. I think I don't know, very fast. You should need finishing it. And we write a paper on that. So that's elastic constant of alumina. Okay. At 0 Kelvin. Then we have to talk about temperature dependent, right? We calculate temperature dependent of elastic constants as from for oxide. Of course, now you look at literature, elastic property calculation, last 10 years is booming. And so many papers on the elastic property calculation for different compounds. And then we also work on the dislocations, core structure. We had the 2 papers, and then we had 3 papers on this one. Now this is much later, right? 10 years after that, because it's a lot harder. And then we also work on the relative creep rate. That was one of our students. That work was done like 2012. Took many years to finish the paper. Students gradually left our group, and she had 2 kids, and become professor. Now she realized the professor is important to have papers. So they got a paper published. That's good. And then this paper is with Professor Bees. And on this, this is not, this one is not. This is, yeah, same, both of them. One is for the stacking process, I believe. And nickel 3 aluminum. And this one's pure nickel. Okay. We now have the third paper come up is for the alloy, nickel X. Okay. Then we have the fourth one is on polycrystal. Okay. So I feel lined up in that direction. And we also work in the hardness. And unfortunately, we have not get it finished yet. It's still working on that. Okay. It's also with the plastic deformation into the model. Okay. I think that would be very, this could be both have going to be interact each other. That's all I have for this approach we have. I have a few more slides. I'm going to back up there. I'm going to put it there for people to use. Actually, we'll talk about the semi-electric coefficient prediction. And that's really, I think, very exciting to me because we can predict these properties. People always think it has to do by kinetic simulations. Okay. I also have a few slides here talk about why you should do a genome. And I showed that you can actually use human genome, very resemble. This resembles a human genome, so to speak, and talk about the last slide. The question I have is, what are the base pairs for phase? I think we found it, and we think that's what we can predict it. All right, 30 minutes. Wow, no, it's less than 30 minutes. 25 minutes. That's good. Okay, Wes, please turn off the recording. Thank you.